Alrighty, let's take a look at some of our inclined plane friction problems as well as our first outward machine. All right, this question has some different things on it. We're going to squash all of it into the free space that we have right here. All right, let's begin with the free body diagram. So we know we're going to have gravity going this way, normal force going this way. Our question tells us that we are ignoring friction, so hooray for that, which tells us that we really only need to have two components here. We need our mg cosine theta, that is our component opposite the normal force, and we need our mg sine of theta. Theta, of course, being right there. Same breakdown we have done for every single darn thing on an inclined plane. So that is kind of an important one for us. Now, find the acceleration of the car down the hill. Okay, let's consider what the heck is making this go down the hill in the first place. We're ignoring friction, so the only force actually trying to go down the hill is this one. Okay, bigger minus smaller, we don't have smaller, I guess is where I'm going with this. So when we say MA, when we say bigger minus smaller, let's start with bigger, and there is no smaller. There we go. If we want to know the acceleration of this thing going down the hill, let's see, we can cancel out that. So the acceleration is going to be very simply g, or 9.81, times the sine of our angle. When you do the math and you figure that out, you should get about 8.89 meters per second squared, which is pretty big. But this is kind of a crazy inclined plane, right? All right, second question. What time does it take to reach the bottom of the hill? Okay, we're going back to kinematics here. So we're going to work with a VT graph. We know this is starting from rest according to our question. The 8.89 is the key piece that we need for the velocity time graph. It's our acceleration, it's our slope of the line. All right, the key things that we are missing. We do not know VF, we do not know TF. Okay, but we do know that acceleration is equal to VF minus VI on TF minus TI, and we know that those two are zero, so they're going to drop out. So if we consider 8.89 TF equals VF, we can work with that. We can't get very far quite yet, but we're missing another piece that we never really put down, and that is how far the roller coaster is going down the hill, which is our 20 meters. So when we consider the area of our triangle being 20 meters, and that is 1/2 VF TF, I'm going to move the 2 over, multiply both sides by 2, because I think that makes it a little bit easier. I'm going to take this and I'm going to put it right there and plug it in for VF. So I get 40 equals 8.89 TF squared. When I do the math, the next thing I'm going to do, divide by 8.89 on both sides, right? Get TF squared by itself. I'm going to write all over this thing, right? That is just kind of a mess. I get 4.49, and then when I do TF, I take the square root. I should get 2.12 seconds, and there's the second piece of my answer. All right, so there's my first one. There's my second one. Hopefully that helps. Remember, you can always go back if needed. All right, box being dragged across a rough floor by a large spring. So consider a spring, and there's this force being applied by the spring, right? And what do we know those forces are called? Oh my gosh, it's a spring force. It's been a while, but we know that one. All right, we still need the rest of our free body diagram. It would totally help us out here. And since they say it's a rough floor, we're going to assume we have a force of friction going the other way. Okay, the spring is stretched 2.5 meters, and it has a spring constant of 100 newtons per meter. Remember, that is a measure of how stretchy things are. All right, we've got a coefficient of friction of 0.9, but don't be fooled. That's not a force. All right, not a force at all. Let's figure that the box is going to be, oh, well, the box is moving. How much time will it take the box to move 100 meters if it starts from rest? Which tells me that there's an acceleration here. These forces are not balanced, and my guess is going to be that the spring force is bigger than the friction forces. So let's figure out what that spring force is. That's going to be our first one. All right, so force of a spring is equal to kx. So we're going to take 100 newtons per meter times our stretch of 2.5 meters. Remember, if you're dealing with centimeters, you're going to have to do metric conversions, just not today. So 250 newtons is my spring force. And my friction force, if we want to find that, and we know mu equals friction force over normal. So mu Fn equals Ff. So what that means to me is if I can figure out the normal force, which luckily in this case will be the same as the mass times gravity, then I should be all good to go. All right, so let's figure this one out, right? mg is going to be 25 times 9.81. I should really change colors there. That would make life a little bit easier for y'all, but I mean, we're doing the best we can here. Let's see, 25 times 9.81 is 221 newtons right there. So now let's consider the big picture. All right, I know that the 221 newtons is that it's the same, right? Because they're equal and opposite to each other. There's no other forces going up and down. So let's go consider mass times acceleration, or net force, is going to be equal to the bigger force, which is the spring force, minus the smaller force of friction here. All right, so 25 is my mass in kilograms times acceleration equals my 250 newtons minus mu, right, mu Fn. Mu Fn, that's 0.9 times 221, because that's the normal force. So I end up with 25A equals 250 minus 251, or 250 minus 221, excuse me, is actually 29.28. My acceleration turns out to be 1.17 meters per second squared. Second question asks, how much time will it take to move the box 100 meters if it starts from rest? Okay, so I'm going to erase a little bit here so I have some space to work, because now we have the key stuff that we need. If you needed that information, I would say pause, go back, and then go ahead and take a look from there. All right, I'm going to actually switch back to black. VT graph looks like this. It's starting from rest. My acceleration is 1.17, and it is moving 100 meters. This is exactly like the roller coaster question. The way we're going to solve this is going to be identical to that. So the 100 meters, that's my area under the curve, is 1/2 VFTF. I don't know either one of those. Sorry, I'm trying to make that, this isn't calibrated properly, so I can't see what I'm doing on some of these. All right, there we go. And that's supposed to be a 0. All right, so 100 equals 1/2 VFTF, so 200 equals VFTF. The slope of my line is my 1.17, and that's going to be VF over TF, because again, those initials are 0. So I'm going to take that, I'm going to put it right there, and I'm going to do some algebra. I'm going to assume you can do algebra, and eventually you can check your math on this, and if you can't get it to come out, come see me. 13.07 seconds is going to be your final answer when you do that. Okay, so check your work, pause the tape, finish the math. If you cannot get it, come see me and I will help you with any mistakes that you are making. Here's our last one, and this is a newbie, an Atwood machine. Okay, so the key thing about an Atwood machine is there's always a pulley in there, and the function of the pulley is to change direction. You may remember this conversation. All right, we are ignoring the pulley, which is what this means over a frictionless pulley. It means we don't have to worry about the pulley itself, we can ignore it. The key things we need to realize is that there are two objects and they are connected by the same rope. So there's a tension there, and the tensions on each side of the rope are the same. The acceleration of each block is identical as well, and this helps us tremendously because the way to solve these is to make two different free body diagrams. Okay, now just based off of logic alone, if I'm ignoring the pulley, it makes sense to figure that it's going to go this way, right? This one's going to go down because it's heavier than the other one. So my acceleration is going to go in this direction. And that's important because it's going to allow me to do each block individually. I'm going to call this block 1 and I'm going to call that block 2. Okay, so the first thing I'm going to do, and I'm going to strongly suggest, is you make free body diagrams for each block. Okay, so gravity, tension, they seem to be the same, but we're going to actually analyze these quite differently. And let's face it, M1 and M2 are not the same, so these values are not the same either. Okay, so if I were to do an equation for each one of these blocks, I'm going to get some different things, right? I know I can do net force, or bigger, or M1 times the acceleration, net force, equals the bigger force minus the smaller force. Well, I know that block 1 is going down, so I know M1G has got to be bigger than the tension. Makes sense, I hope, right? It's going down, so that's got to be bigger, and that's got to be smaller. Now, if I look at the other block, I'll do this one in red, this block is going this way. It's going up. So M2A, right, net force, equals bigger minus smaller. Tension is bigger, M2G is going to be smaller. So I have two different equations. And the key thing here, of course, is that the acceleration is the same and the tension is the same. Now, when we are in AP Physics, what I have everybody do is line the equations up. It's a way of substituting, right? You guys usually like to substitute, but something that we can do is add the equations together. That's another way of substituting the equations. And what happens is the tension cancels out and you end up with M1A plus M2A equals M1G minus M2G, which looks scary. But the truth is the only thing you don't know is the acceleration. You have numbers for everything else. What you guys tend to do is you tend to substitute one equation into the next, and that's fine as well. We'll still get the same answer. Since that is something that you tend to do, I am going to do it that way. But I really have no preference at all. I'm going to rearrange this one for tension because, see, it's already positive, and I kind of like that. So M2A equals tension minus M2G. I'm going to add over the M2G. And then what I would do is I would take this, and just like we've been doing all along with the velocity stuff, I would put it right there for where tension is. Okay, so I'm going to rewrite that in black. So if you're not going to add the equations together, try this technique and substitute. We still have two missing variables, so just remember there's a negative here, so we got to be careful. M2A plus M2G. You have to distribute that negative to both sides, and we want to get the acceleration by itself. So M1A equals M1G minus M2A minus M2G. To get the A by itself, take this and move it to the left-hand side. All right, I'm going to give myself a little more room here to work. All right, M1A plus M2A equals M1G minus M2G. I'm just moving things around. I can pull out the A because it's common to both. That should be a plus sign. I don't know if this is going to let me show you a plus sign. All right, and then divide. Divide by the M1 plus M2. Okay, so now that looks really scary maybe, or a little complicated, but really let's think about this. Let me go back to red. You're solving for A. You have managed to isolate it because I know you can't see it here, but these have canceled out, right? So you get A equals. And this, even though it's complicated, you know every single number that goes in there. So it is not a big deal. When you plug those numbers in and you do the math, you're going to get 0.239 meters per second squared. So try it out. And if you can't figure it out, let me know. Your last part here is then to solve for tension. And since I'm out of room, there's not a whole lot I can do here. But what I would say is pick one of your equations. I don't care really which one, they'll both work. But plug in your acceleration and plug in all your other numbers and solve for your tension. And you should have it. All right, and just to give you an idea of what this answer is so that you can try it on your own, 50.5 newtons. Okay, I had to skip a few steps there for space, but hopefully that makes pretty good sense. Let me know if you have any questions.